Okay, today we are going to talk about sequential experiments. That is chapter 2 from the textbook. Here is the outline of the presentation. 3 diagrams, counting methods, independent trials, and reliability analysis. Let's start with 3 diagrams with an example. First of all, 3 diagrams simply a way to display the outcomes of a sequence of experiments. Usually they are called sub-experiments. And we can see probability values, conditional probability values using the 3 diagrams. In this example, you see we have a timing of 2 traffic lights. Let's say the first traffic light here and then here. So we have a road, let's say, going through here. This is traffic light 1 and 2. So what happens? First, we come across traffic light 1. Then we might have, for traffic light 1, we might have a green or red. Okay. If this green, we pass through and then come across traffic light 2. Then in the next traffic light, there may be a green or red. And if there is a red in the first traffic light, then we wait and then we continue. And then the next will be again red or green. Okay, so we can use the indices here. Let's say the first traffic light, it could be green 1, red 1, and the second one green 2, red 2, green 2, red 2. So this is the problem, and this is how we draw a tree for this experiment. Now, in this experiment, traffic engineers have coordinated the timing of 2 traffic lights to encourage a run of green light. So once you got the first green, then the next, the likelihood of having the next is a green is quite high. Okay, this is usual case, and it's given us 80% here. So if the first is green, then the second is also green with the likelihood of with probability of 80%, so 0.8. This is how they design. Assuming the first light is equally likely, so whether you come across with green or red are equal, which means that 50%. So we can put here, let's say 0.5. So the first light might be green with the probability of 0.5 or red with probability of 0.5. And what is the probability of G2? So the second light is a green. What is the probability of W? Probability that you wait at least one of the lights. And what is the probability of G1 given that R2? So what is the probability that you get a green light given that the second light is a red? Okay. In next slide, we have the solution actually. And you can see all probability values. You see the first light might be 50% green, 50% red, And if this is green, the next one is green with 0.8. Probability 0.8 is given here. So green, green, or red, red, 0.8 again. Then the other will be 1 minus, simply 1 minus 0.8, which is 0.2. Okay? So the branch of a tree here is always equal to 1. Okay? According to probability axioms. Now, let's see probability of G2. Probability of G2 will be combination of all the outcomes here where we got probability, where we got a green 2. Here we see this is green 2, this is green 2, so probability of this one and this one, sum of the probabilities of this, which is 0.5. So what's the probability that you weight at least one of the lights? And we have to take into account the outcomes where we have at least one red. Okay, we see that this could be red 1, green 2, green 1, red 2, and red 1 and red 2. So the union of this will give us probability of weighting at least one of the traffic lights. So we simply add them up. Probability of R1G2, G1R2, R1R2, which makes 0.6. So 60%, then when you derive to this rod, 60% you will get at least one red. Alternatively, we can calculate probability of weighting at least one light as the complement of the even, green, green, because there is just one outcome where there is no red. So the complement of this will give us simply weighting at least one light. So this could be maybe easier. 1 minus probability of G1, G2, which is again 0.6. How about the conditional probability? Remember the formula for conditional probability. So the green one, given that the second light is a red, it's going to be probability of G1 R2 divided by probability of R2. So here we have to determine probability of R2 first, which is unknown. Probability of R2 will be simply 1 minus probability of G2. Okay? Or alternatively, we can take the outcomes, including R2, so this one and this one, which is 1 minus probability of G2, which is 0.5. So we insert this into here. This is already known. So probability that G1, given that R2, is simply found to be 0.2. So 20%. Next, counting methods. Counting is simply a way to estimate the elements of sample space, so outcomes of sample space. If we have a sequential experiments, we can start with the theorems. If we have two sub-experiments, okay, two sub-experiments, so sequential experiments, if the first sub-experiment has K outcomes and the second sub-experiment has N outcomes, then the experiment has N times K outcomes. Okay? N times K outcomes. That's quite easy. If you have two sub-experiments, one has K outcomes, the other one is N outcomes, then the experiment will have N times K outcomes. The number of K permutations of N distinguishable objects is written here, the number of k permutation of n distinguishable objects is simply n times n minus 1, n minus 2 goes to n minus k plus 1. Or simply n factorial divided by n minus k factorial. Okay? Let's see examples of these theorems. Okay, we have two sub-experiments. One is the first one. Flip a coin. The second one, roll a die. Okay, the first one will have head or tail. The second one will have 1, 2, 3, 4, 5, and 6. So the total number of outcomes for the first sub-experiment is 2. The second sub-experiment has 6 outcomes. So the total number of outcomes will be 2 times 6. Simply, this is k, this is n, so n times k. Okay? Next, we have a deck of cards, 52 cards. Okay? And we choose 7 cards from this deck. How many different sequences of cards are possible? Okay? If we, let's think about this. Let's say we have 52 cards and I choose one, then there's going to be 51 cards. I choose another one, there's going to be 50 cards. And then 49, and then 48, and then 47, and then 46. So I choose 1, 2, 3, 4, 5, 6, and 7. So the first card will be any of the 52 cards. Okay, so I have 52 different choices, possibilities I have. So 52. Next, once I choose one, there's going to be 51 cards left. So the choice of the next, so the number of variations, number of sequence for the next card is going to be 51. So times 51. Next, 52. So sorry, 50, 49, and 48, and then 47, and then 46. So then the multiplication of this sequence will give you the number of sequences that could be possible in this experiment. So we can simply here use the formula, right, in previous slide. Remember that it was, right, simply k permutations of n distinguishable objects. So n to n factorial n minus k factorial, okay? So then it's going to be 52 factorial divided by 52 minus 7, which is what? Which is 55, okay? So it's going to be 52, 51, 50, 49, 48, 47, and 46. And 45 will be cancelled. So this multiplication, which is equivalent to this one. Next, we have a definition. This is called n choice k. So we choose k. So the number of k combinations of n objects, which is called n choose k, and it is given n factorial divided by k factorial n minus k factorial. Okay? So one sense this could be then nk divided by k factorial, right? This is equal to this one. So sampling without replacement. If we have n distinguishable objects and we look at the number of ways to choose k objects out of this n distinguishable objects, we use n choose k. Okay? N choose k, which is again nk over k factorial. Okay, let's see this example. We are given A, B, C, D. So 4 letters. And we define an experiment where we choose 2 objects without replacement. Okay? So when I choose one object, I couldn't replace it. And we arrange them in alphabetical order. Observe the results. Then I might have these possibilities: AB, AC, AD, right? Starting with A. The next letter is B, so BC and BD. Next, CD. So the total number of outcomes is simply 6. So what does it mean? So we choose 4, so 2 from 4, right? 2 out of 4. So we can simply use this formula. Sampling with replacement, given m distinguishable objects, then there are m to the power n to choose with replacement and order sample of n objects. So we choose n objects, ordered sample of n objects for out of m distinguishable objects. Here, example 213, we see a binary sequence. You can consider a binary sequence of length 10. So just like, for example, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So 1 to 10. So 10 bits. Okay, so how many different sequences we can create like this? Okay, from, you see, 1 and 0. So it will start with 0, 0, 1. I'm sorry. One, and then 0, 0, 1, 0, 0, 0, 1, 1. So it goes like this, and finally we got 1, 1, 1, 1, 1, 1, 1, 1. Okay? So how many such sequences can we create? Simple. Since we have binary, so we have 2 to the power 10, which is 1024. If it were 2 bits, then it's going to be 2 to the power 2, which is 4. So 0, 0, 0, 1, 1, 0, 1, 1. Okay? Next example, it's about microprocessors. We have a chip fabrication facility that produces microprocessors. Each microprocessor is tested to determine whether it runs reliably at an acceptable clock speed. A sub-experiment to test a microprocessor has sample space. So C sub-experiment has a sample space of 0 and 1. So 0 means that the test was a failure, and 1 means that the test is a success. So I just take a microprocessor and then test it, whether it is acceptable, it has acceptable clock speed or not. If it is not, then we simply say 0. And if it is successful, we simply say 1. So suppose that we test such microprocessors in order. And for any ith test, the outcome is xi. So it could be either 0 or 1, one of this. Now, let's take 4 microprocessors. So I, then could be 0, 1, 2, and 3, or I could be 1, 2, 3, and 4. Then I will have 4-bit sequence, right? So let's say x1, x2, x3, and x4. So it could be 0, 0, 0, 0, or 1, 1, 1, 1. So then we'll have 2 to the power of 4, right? 4, which is 16. So the sample space of this experiment is going to have 16 outcomes. Okay, the next theorem, we have a sub-experiment with this outcome, set of outcomes. So S sub has S0 to Sm-1. And we have n repetitions of this experiment. And then the sample space will have m to the power n outcomes. So example 216 is about that. We have a probability course, let's say our course, EE213 in summer school. I have 4 students, okay? And we give letters, right? Letter grades, starting with AA, BA. Let's say these are A, B, C, D, and F. Okay, and also NA, for example. So how many? We have 1, 2, 3, 4, 5, 6, and 4 students. Okay? So it is going to be what? How many repetitions do we have here? We just put the students in order, right? For example, A, all students might take A, or all students might take F, right? Or let's say B, A, D, F. So all the variations of this, which is then 6 to the power 4, okay? The number of outcomes. Next theorem is again about the number of observation sequences for n sub-experiments with the same with the sample space of 0 and 1, and 0 appears n0 times and 1 appears n1 times. Okay, so 0 appears n0 times and 1 appears n1 times. So the total number of experiments is n, which is n0 plus n1. Okay, so the number of observation sequences here could be then n, n1, or n, n0. Okay, let's see example 217. We have 5 sub-experiments with sample space 0, 1. What is the number of observation sequences in which 0 appears n0 2 times and 1 appears 3 times? So we have 5 n, right? How can I find this? I simply use this one, right? So it's going to be simply 5 choose 2, right? Or 5 choose 3. This corresponds to n, n1, and this corresponds to n0, n choose n1. We then determine the number of outcomes using the formula in previous slide. Okay, multinomial coefficient. Now, previously we talked about n choose k. Now here we have n choose n0 and m minus 1. So we have multiple k's in here. And this is given simply n choose n0 and m minus 1. This is equal to n factorial divided by n0 factorial, n1 factorial, and n m minus 1 factorial. So multiplication all the factorials or the values of n I factorials. For n repetition of a sub-experiment with sample space, the number of length n observation sequence with Si appearing ni times is given with this formula. Okay? Now we can use example 16 in previous slide to demonstrate how to use this equation. We have again letter grading in probability course, and here there are 10 students. So 10 students in the probability class, and 2 students take A, and 3 students take B, and 3 students take C, and 2 students take F. Okay, so how many different ways can the professor assign grades to the 10 students? So how many different variations of this letter grading? That's the question. So here we have 4 different values. So we have N0, N1, N2, and N3. So it seems that our M is going to be 4 here, right? So we simply write this equation by inserting this N1, N2, and N3 into here. And then that's going to be 10 choose 2, 3, 3, 2. Okay? Which becomes 25,200. Independent trials. These are simply identical sub-experiments, and we have again sequential experiments, and the probability model for each sub-experiment is independent and identical of the outcomes of other sub-experiments. Sampling with replacement is one of the category of experiments with independent trials. In general, we have n independent trials where we have n0 failures and n1 success. And the probability of each outcome in this case is going to be 1 minus p to the power n0 times p to the power n1. Here, p is probability of failure of one trial, and so 1 minus p is going to be the success of one trial. So there are n choose n0 outcomes that have n0 failures and 1 success. Then we define the theorem. Probability of n0 failures and n1 successes in n independent trial is given with this formula. Okay? So simply we, for example, say probability of E, 2, and 3, which means that I have 5 trials and 2 are failure, 3 are successes. So what is the probability of this? Or probability that E7 to 3. So I have 10 trials total, 10 trials. Okay, here's 5. And 3 failures and 7 failures and 3 successes. An example. This is a communication system example. Typically, in communication systems, when we transmit binary 1, here's the transmitter, let's say, here's the receiver, we expect that we get 1. But due to the error in the channel, this may be received as 0. When I transmit 0, normally I should receive 0 at the receiver side, but due to the errors in the channel, there may be 1 I receive here. So there may be an error. In order to reduce this error, instead of transmitting just 1, in some systems we use encoding, and instead of 1, we transmit 5 ones. Okay? And we count the number of ones at the receiver side. If the number of ones is greater than 3, for example, or 2, then I decide that binary 1 was transmitted. Otherwise, I simply conclude that binary 0 was transmitted. So here we have an example. We transmit 5 ones for binary 1, okay, and for 0, 5 zeros. Okay, and count the number of ones and zeros. So the rule is that the receiver detects the correct information if there are 3 or more binary symbols. So if, for example, 0, 0, 0, 1, 1, so I decide that this is 0. If I have 1, 0, 1, 1, 1, so I decide that that's 1. Okay, because the number of ones is 4 greater than 3. So the question is, what is the information error probability, PE? Sorry. PE. PE is going to be simply, I transmit a sequence and I count the number of bits. If the number of failure is less than 3, then I might not have any error. If it is greater than 3, then we got error. So we can simply look at the combinations of E0, 5, right? So there is just, there is no there is no success and all are failure, plus E14 and E23. So the probability of these cases will give you the probability of error. Okay? But here we have to know the symbol error probability. I mean, if I transmit 0, what is the probability that you get binary 1? It's given Q is 0.1. So 10%. If I try this with a single bit, out of 10 times, 10 tries, only one of them was received incorrectly. This is how we read it. Now, then I can determine this probabilities to find the error probability, which is 5 choose 0 and Q to the power 5, using the previous slide's equation. 5 choose 1, P Q to the power 4. By the way, P is going to be 1 minus Q, which is 0.9. Okay, so probability of, you see, the probability of receiving 0 when we transmit 0 is 0.9. Here is 0.1, here is 0.1, and here is 0.9. Plus, next, 5 choose 2, P to the power 2, and Q to the power 3. So we can determine this. So it is 0.9 0.00856. So the error that we may make when we use 5 bits instead of single bit to transmit symbol 1, the error normally was 0.1, right? This was the error. Now this error reduced to this one. Okay? So it's quite, you see, a safe method to transmit binary symbols. Theorem 2.9. A sub-experiment had sample space, this one, as usual, and probability of any outcome here is pi. For n independent trials, the probability of ni occurrence of Si is given with this formula. Okay? And we show this using an experiment, using an example, sorry. A packet processed by an internet router carries either audio information with probability 7/10. So let's say audio with probability 7/10. Video with 2/10. Or text with 1/10. So the total here should be 10/10 because this simply composes the sample space. Now let's define an event. Let's say E A V T. So the audio, video, and T. So A audio packets, V video packets, and T text packets in a sequence of 100 packets. Okay? What is the probability of AVT? Probability of EAVT. So we use this formula. It simply says 100 AVT, so 7/10 to the power. So this was the probability here. PA, let's say, this is PV, this is PT. So this is PA to the power A, the number of audio packets, 2/10 to the power V, the number of video packets, which is PV here, and 1/10, which is the probability of text packets. So we can determine probability of AVT. Okay? Okay, reliability analysis in text, in lecture notes, you may not find this material, but I think that this is an important material, so I just want to talk about that a little bit. We have a complicated process here, and this process might be divided into some components connected in series and parallel. This methodology is quite helpful to determine the reliability of the system. Suppose that we connect 3 components in series. So, and let's use Wi as the event that component I succeeds. Okay, I succeeds. So this is W1, the first component, second component, third component, and success of the first component, success of the second component, and success of the third component. So the overall probability of success here will be simply multiplication of all this, so the intersection of these successes, and then we have to know then the success probability. If the success probability of component 1, 2, and 3 all are equal, then it's going to be simply p times p times p, so the number of elements. If there are n elements, then that's going to be p to the power n. If each component has a different success probability, let's say p1, p2, and p3, then probability of success for this system is going to be simply p1, p2, and p3, so pn. What happens if we connect them in parallel? If it is connected in parallel, we can define a probability of failure as the complement of the success, which is going to be the same as this one, except that here we can define Q, probability of failure, as, Q as 1 over P. Then that's going to be simply Q to the power n. So it's going to be Q to the power n. So probability of success will be 1 minus probability of failure, which is 1 minus P to the power n. Or we can write P 1 minus Q to the power n, where Q is the probability of failure for each component. And all components have the same success probability. If they do not have the same success probability, then we have to write each of this, which is going to be given like this. Okay, a little bit complicated. We can convert this into simply, we can take, for example, Q1, Q2, Qn as the failure probabilities. Then there's going to be Q1, Q2, and Qn. Let's complete today's lesson with an example. We have an operation of two redundant parts. Redundant parts means we connect two parts in parallel. Okay, the first part has two components in series. So I got one component series connected in series with the second one. Okay, this is the first part. The second part is simply redundant, so it's going to be connected in parallel with this. So here is the system model. And success probability is given as 0.9. Draw a diagram of the operation and calculate the probability that the operation succeeds. So to find the probability that the operation succeeds, we can obtain an equivalent of this. So these two are connected in series, and then we can use this a single component, let's say W5, and here another one, where we may define W6. So this could be simplified to this parallel combination. Okay. Now we have to determine probability of W5, which is a series connection. So it's going to be probability of W1 and W2, which is P times P, so P squared, which is 0.9 squared, so it's 0.81. So probability of W6 is the same, right? That probability of W5, because success probabilities are equal. So it's 0.81. Now, if you look at the entire operation, since these are connected in parallel, then I can define probability of success as 1 minus probability of failure. okay, which is 1 minus p 5 to the power 2, which is 1 minus 2 5 squared, if we define Taylor property. Okay, so that's all about on sequential experiments. It's enough for today. Do you have any question?